Now let us consider a nonlinear circuit, a circuit with a two terminal nonlinear element such as a diode, and see how to analyze it. And let me take this circuit with a voltage source, a resistor R and a diode. Okay. And of course, this could be any other nonlinear element as well. Okay. I will call the voltage across this Vd and the current through it as Id. Okay. Let us see how to analyze this. Now, a linear circuit with the same structure is to have R and R1. Okay. Now, of course, this one, after you have done your basic electrical circuits or even maybe before, it does not even require a moment's thought, right? You know what the solution is. It is just a resistive divider. Now, we will see how to solve this, and you will understand that the analysis of nonlinear circuits is considerably harder than linear circuits. Okay. So, now really this is an extremely simple circuit. So, this is an independent voltage source, and all we have to do is to write KCL at this node. Okay. That will give us the solution. So, KCL at that node says that the current flowing through R in this direction equals Id, which is current flowing through the diode in the downward direction. Okay. Now, the diode itself tells you that Id is f of Vd. This is the general case for any nonlinear element, and in case of the diode, it is Is exponential Vd by the thermal voltage minus 1. Okay. And the current in the resistor R, this equals Vs minus Vd, which is the voltage across the resistor divided by the resistance value. Okay. So, our KCL equation simply says that Vs minus Vd by R equals f of Vd in case of a general nonlinearity, or in the specific case of a diode, it is Is exponential Vd by Vt minus 1. Okay. Now, there is only one variable here. Vs is the source, we know that. The only one variable is Vd. Okay. So, all others are parameters of the components. R is a parameter of the resistor, and Is is a parameter of the diode, and Vt is a fundamental constant. So, you may be familiar with solving nonlinear equations. You may be familiar with methods like bisection method or Newton-Raphson iteration and so on. Okay. So, if you do, then you know how to solve this numerically, and you know that unlike linear equations, there is no general inversion formula or general solution formula for nonlinear equations. Okay. So, if you have a set of linear equations, by a matrix inversion you can find the solution, but for nonlinear equations there is no such general method, and depending on the type of nonlinearity you may have to choose different methods. Usually the solution is numerical, and there may be multiple solutions, there may be no guarantee that you will reach a solution and so on, but usually the way to solve nonlinear equations are numerical and iterative. Okay. Now, of course, in this course we will not go through that, we just assume that the solution can be found somehow. Okay. What we will do is to bypass explicitly solving the nonlinear equation, at least for hand calculations. Okay. So, this can be solved numerically. Now, what is also useful for engineers is to find the solution pictorially or graphically. This is for the sake of visualization. Okay. Now, usually you don't do graphical solutions when you want accuracy in the solution, but you do it when you want to visualize the behavior. Okay. So, let us do that now for this particular circuit. Now, that technique is also limited. Okay. So, when you have too many variables, you can't draw multidimensional graphs. Okay. In this particular case, it turns out you can do it because you have only two variables, one voltage and one current. Okay. So, the equation to be solved is Vs minus Vd by R, which is equal to Is exponential Vd by Vt minus 1. Okay. So, what I can do is I can essentially plot the right hand side and left hand side separately. Okay. So, there is some function on the left hand side, there is some other function on the right hand side, both are functions of Vd, which is my independent variable, and I can find the point of equality or the point of intersection, that will be the solution. Okay. Now, the right side is nothing but the diode current. So, that is why I have marked it as ID versus Vd. So, plotting the right side simply means plotting the diode characteristics, which are like that, it is the exponential. Okay. And plotting the left side, that is what I want to plot is Vs minus Vd by R versus Vd. Okay. So, this is just a straight line, you can see that this is a linear function of Vd. So, when Vd equals 0, this function will be Vs by R, and when Vd equals Vs, this function will be 0, and it is obvious that it also has a negative slope, and the slope is minus 1 by R. Remember, Vd is the independent variable here, and the coefficient of Vd in this function is minus 1 by R. Okay. So, very easy to plot also. So, when Vd is 0, it is Vs by R, when Vd equals Vs, it will be 0, and it will be a line, straight line connecting these two points, and the slope of this is obviously minus 1 by R. Okay. Now, clearly in this case there is only one point of intersection, and that is the solution. Okay. Now, if you solve this equation numerically, you would find this value of Vd, and if you find the value of the current corresponding to that, that is Vs minus Vd by R, or this side, it will be this value of current. Okay. So, this is the solution. So, by plotting different parts of the equation and finding the point of equality, that is finding the point of intersection, you can find the solution. Okay. So, say somehow you find the solution either numerically or graphically. Now, I will just give you an illustration. If you want, you can solve for this numerically and find the solution. Okay. So, let me take a case where Vs is 5.7 volts, R is 5 kilo ohms, and the diode has a saturation current of 10 to the minus 15 amperes. Now, it turns out that if you solve this numerically, you will find that Vd is approximately 0.72 volts, and the diode current is approximately 1 milliamp. Okay. That is the solution. Okay. Let us say we have solved it for a particular value of Vs, which is 5.7 volts, and now the value of Vs changes. Okay. So, let us say it becomes 6.7 volts. So, what you have to do? You have to solve this all over again. That's pretty clear, right? So, with let us say this particular curve, whatever I have shown here, this is the part, the straight line is what is dependent on Vs, right? In this particular case, this exponential, the right hand side of it is independent of Vs. It happens to be so in this particular case, and the left hand side is dependent on Vs. It is this line. So, let us say this particular one which I have already drawn corresponds to Vs equals 5.7 volts. If you change the value of Vs, what you have to do? You have to redo this. Okay. So, let us say Vs changes to 6.7 volts, you will get a line like that and you will get a different solution. So, let us say Vs is 6.7 volts, or alternatively if Vs is 4.7 volts, you would get a solution like that, okay, and you will get yet another solution. So, this corresponds to Vs equals 4.7 volts. So, the point is that anytime the input changes, you have to solve the nonlinear equation all over again. Okay. Now, this is a big difference from linear circuits. Okay. So, if I go back to the linear circuit I showed earlier, again this is extremely simple, and if you want to solve it, you can do it from scratch also, right. So, in this case, let us say you knew the solution for Vs equals 5.7 volts. Then if Vs changes to 6.7, you know that the new solution is simply proportional to the new value of Vs. Okay. So, linearity holds. Even when you have multiple sources, the solution will be linear combination of all the sources. So, if you find solutions, if you find the solution to the circuit for one particular value of Vs, you can find it for any other value simply by scaling. Now, in case of nonlinear circuits, first of all, finding the solution is very complicated. On top of it, if you change the value of Vs, you have to go through the nonlinear calculation all over again. Now, this case where the input is changing is a very relevant case for us, because we want to amplify some signals in our amplifier, okay, and a signal usually is a time varying signal, okay. That is, when I am speaking into the microphone, it is giving a time varying voltage to the circuit. So, we have to be able to analyze our circuits with varying inputs, okay. So, I will show the same example with, let us say, two sources in series. So, this could be, let us say, a 5.7 volt source, and this could be a sinusoidal source, okay. This is what I call a signal. This could be, let us say, some 100 millivolt sine omega t, or maybe 1 volt sine omega t, okay. Now, if you wanted to find Vd in this particular case, what will you have to do? So, the way I have set it up, the circuit is exactly the same. So, the voltage source that is applied to the circuit is now time varying, okay. So, this is the Vs, right, this is the value of Vs, and Vs in this case is 5.7 volts plus 1 volt sine omega t, and if I plot Vs versus time, it will look like that. The maximum value will be 6.7 during positive peaks of the sine wave, and minimum value will be 4.7 volts, okay. So, how would you find the solution or the response Vd to an input like this? You would have to find it for 5.7, okay. There is some value of Vd that you get, that you see from the previous graph. So, this is the value for 5.7. You would have to do it for 6.7 and 4.7 and so on, and also many points in between, okay. So, essentially this is Vs, you have to keep varying Vs and keep drawing these straight lines, find the solution and plot the solution Vd from that one, okay. So, there will be some solution here, something else for 5.7, something else for 4.7, some other solution for intermediate values and so on. Okay. It is extremely cumbersome, and you can feel that to get a reasonable plot, you have to take many points in this cycle. Okay. So, first of all, finding the solution for each point is very tedious, and doing it for so many points, this is just next to impossible. Okay. So, you can find Vd like this in principle. Okay. We know that value of Vd when the input is 5.7, that is about 0.7 volts. Okay. So, the 0.72 volts, so that is what I said, and when it is 6.7, you can calculate it numerically. It turns out to be something slightly higher, and for 4.7 it will be something slightly lower, and you can calculate the intermediate points and find that the solution looks somewhat like that. Okay. Now, this, while okay in principle, is simply not practical. So, what we will do is to find an alternative way of analyzing nonlinear circuits, which is approximate, but at least something that we can carry out by hand, and that we need to be able to do in order to get any insights into our circuits. Okay.